Pleasure to restart the colloquium session, the regular colloquia of the Wednesday. So our first speaker for this new season is Cristina Chiappini from Leibniz. And I'm going to introduce a little bit her background and her career. So she got her PhD in Sao Paulo in 1998. She's Brazilian, but she's also Italian. It's important to specify. After a postdoctoral position at the Columbia University, she finally got, not finally, but she got a permanent position in Trieste, right? In 2003, but this permanent position at the end was just 2 years. So after 2 years, she moved to another place.
It was permanent.
No, it was permanent, but you decided that was not permanent. So she moved to Geneva as a maître assistant, and then she got another permanent position in Potsdam in 2011, and she's still there. Now, she has a very long established track record in chemical evolution, chemodynamics, nucleosynthesis, and she has a vast experience with models and large data sets, right? And she has been leading large projects and teams, and among them, the most important, as far as I understand, is she has been the project scientist for the FORMOST, which is a multi-object spectrograph being built by the ESO-VISTA telescope, for the ESO-VISTA telescope. And in her role, she played some crucial role in setting the requirements for the scientific mission and setting the instruments, right, in order to achieve what they hope to achieve. And today's talk is about the Milky Way story told by its oldest stellar populations. You can start.
Super, thanks for the introduction. Thank you all for being here again, the ones that are in the lectures. So I already excuse myself because I'm a bit jet lagged in the afternoon. It's tough. And I also had a bit of a difficult to choose what to present in the colloquium, given that I'm giving 4 lectures. And by talking to people, see more or less the interest. And so I decided maybe to focus on a result that, on several potpourri of results that are linked to the fact that we can get ages for stars quite precisely for the Milky Way. So that's why I put the Milky Way story told by its oldest stellar population, so its oldest stars. I understand that there are people here that are not doing astronomy. So that's the Milky Way. Just look to the sky. Actually, it's one of the reasons why I start doing astronomy. As a student in the school, it turns out that the physics professor offered to give some history of science in the afternoon. And I enrolled that. I was, I think, 15. And then one of the activities was to go to Monte Verde, observe the sky. And it was actually the first time I really saw the sky, because in São Paulo it was impossible. So, and then I was, wow, this is the Milky Way, I want to study this. There is, as you know, recently in most of the fields, there is a big collaborations for things. We cannot do anything by ourselves. So one of the big part of this work is being done with collaborators. Among them, my ex-PhD student, Ana Queiroz, that finished her PhD, is now a postdoc in Canary Island, in the IAC. And Friedrich Anders, who also finished his PhD with me and is now a senior researcher in Barcelona and joined the Gaia group. And the current PhD student, which is Samir Nepal, that is right now with me in Potsdam. So, and of course, a lot of nice, great collaborators, plus the people from the Formidable OR, which is this survey to follow up the Gaia targets with spectroscopy. That's part what we are going to do as part of Foremost. So, because we want to understand why it's important to study our galaxy, I just want to give you a brief idea why, given that you have so many other galaxies to study, why you're sticking to this one. Well, there are several reasons and challenges as well. So when we study other galaxies, outside, nearby, or even at high redshift, now we can, you struggle a bit with spatial resolution, which is getting better and better. So with instruments like MUSE, you can achieve very beautiful spatial resolution in the galaxies for information on spectra and photometry as well. And you also have a problem with age resolution. You can determine age from integrate spectra from galaxies, but then your resolution in age is difficult. You have an idea of who is old, who is young, but not really a resolution in age to tell who is 10 gigayears old, who is 11 gigayears old, who is 8 gigayears old, and that matters, as you see. And when you look to an integrated spectrum, you have a luminosity weighted. And the younger stars, they count a lot because they are brighter. And so this is a challenge where you are in other galaxies, which here the challenges are different, of course. We are inside the Milky Way, who is a disk, and we are in this disk. And so we have a difficulty to have a volume coverage of the Milky Way. We were sitting here and seeing most of the things next to us. We have another difficulty, which is to have age precision for each single stars, individual stars, for which we can get ages, as that's important, because we're going to trace the history of the Milky Way. And we have difficulty in having good age precision, especially for stars that are far away and not in clusters. And we have large extinctions that we have to peer to see the inner regions of the galaxy. However, each of them, of course, have advantages linked to their challenges. In the external galaxy, you have this volume coverage for free. You have a diversity of galaxies. You can study galaxies, elliptical galaxies, spiral galaxies like ours, and you can dwarf galaxies, all kinds of galaxies. And you have a multi-wavelength information also, more easily than in the Milky Way. However, we today are going to be here because here we have these individual properties of stars that we can study, which is really a gift for the Milky Way, ages for individual stars, and all the other information like the velocities, the positions of the stars, how they move, their orbits, and also really these maps, which are multidimensional because they contain all this information, position, velocities, especially now with Gaia, plus the distance, of course, and so the orbits, you can integrate the orbits of the stars, and you also have information on chemistry. So we are sitting here today, okay? So this is the current map we have for our galaxy using Gaia plus photometry plus spectroscopy. We are covering that volume nowadays. We used to be sitting here where the sun is, and now we have extended, so most of the data was concentrated here. Now we are extending up to the bar and beyond. Of course, that sky Milky Way can be transformed into this three-dimensional map. And that today was our lecture, for example, how you do that. And then if you do this, this have one of our most recent maps. Here's the Milky Way. Here's the Sagittarius dwarf. It's a galaxy that was cannibalized by our galaxy. The LMC, the SMC, the Magellanic Clouds, and here the bar of the Milky Way, essentially the disk. Here we are now in a situation where we can have a map of our galaxies like we are doing extragalactic. We are seeing our Milky Way from outside almost, face on here, and edge on here. And here is the core of the Sagittarius dwarf galaxy that was eaten by our galaxy. So that information show you had no spectroscopy, and we need to follow up the Gaia data with spectroscopy. We will have the results I'm going to show you today have already spectroscopy, but that's not enough. We need more, to cover more. And for that, we have been, before Gaia was launched, organizing spectroscopic surveys, really big spectroscopic surveys with a multi-object spectra telescope. And for most, you have more than 2,000 fibers. So in one shot, you take 2,000 and something spectra per shot. And also, it's interesting because you have in the same, the moment you take spectra, take both low resolution, high resolution on the same footprint, which is good, but also gives some complications. So inside, foremost, there are several spectroscopic surveys, extragalactic and galactic. And mine is the formidable low R. The bulge and Milky Way is the coverage of the foremost Milky Way and bulge low resolution survey. And there is another one, which is the high resolution. Low resolution here are spectra with 7,000, more or less, resolution, which means that you have a very large spectral range. And this is good also for the extragalactic people that need that. But we can still do some chemistry with this spectrum, we think. This is what you're seeing here is the VISTA telescope, where the foremost instrument will be installed at ESO. And there you see the beautiful Milky Way again. Now, if I look to our galaxy from above in X and Y, so like if I'm looking our galaxy from above, and I make a map with all the spectroscopic surveys that are already available before Gaia was available. These are the spectroscopic surveys. Here, this one is LAMOST, that's cover more the northern part. So you have all of them. Here is Apogee, arriving here where we see the bar. And you see that there is a lack of data in the south, right? And this lack of data is serious for galactic archaeology because you are lacking data exactly in the inner regions of the galaxy and towards the bar. And that's one of the goals of our survey, is to complement that. There you have proper motions, parallax, you can get beautiful information, but you lack the spectra. So you cannot get the radial velocity. Gaia gives you the transversal velocity, you need the radial velocity to construct the orbital. And that's what we are going to give. But we want to give more than radial velocity. We want to give a chemistry. So this is, just in a second, the foremost instrument specification. It looks like this. Is a 2,436 fibers. Is a 4.4 degrees square field of view. So it's a large field of view. And has the low resolution spectrum going from 4,000 to 7,500. You have also the high resolution spectra with 20,000 resolution, which is okay. And you can obtain radial velocity with better than 1 kilometers per second, which is also important for the orbits. It's not so simple to say, okay, so we have Gaia. Gaia has observed almost 2 billion stars. And I have to choose from this 2 billion the best 10 million. And even there, I'm being pushed to do less because we pay fiber hours that we used. So you have to figure out how to select the best 10 billion stars. Sorry, 10 million stars. I'm already dreaming here. And this is what we try to explain in the Messenger article, where we explain our survey. This is a piece of the galaxy. Here is the bar. So we have one sample that is really covering the bulge inner galaxy. We have one sample here that's called extended solar vicinity. Here is the sun. Around here, why are we here? Because here is the la creme de la creme of Gaia. Is where the parallaxes and the velocity will be amazingly good, especially end of mission. So we'll be sure we have a spectra covering those stars. And then the dynamical and chemical maps, which is the more extended over the Milky Way. The difference between the dynamical and chemical catalog is more in signal to noise only. So the chemistry needs more signal to noise. So we do less targets with more signal to noise, get the chemistry. More targets, lower signal to noise, get dynamic. They get the radial velocity essentially. Okay, so now you see where we are going. So let me show you what we have already, because we cannot, to be there, we had to show what we have already, and then to plan for foremost and win the proposal and to get this going. And so foremost started being prepared 10 years ago. In 2010 was the beginning of this particular thing. But now let's dive into here. So the point is that many are the science enabled once you have these maps multidimensional with the 6D velocity space, positional, and the chemistry. You can do several science, and I will give you a taste. And if you have age, even better. I will give a taste of that. And so that's why I wanted to concentrate here on the oldest stars, to give you some ideas of this. So first of all, what is amazing, I think, is that we can get, just being here, sitting next to the solar vicinity, information about other galaxies, because our galaxy has eaten galaxies along its evolution. And this is amazing, because you cannot get very detailed information from a galaxy that's far away. But the stars of these other galaxies are here. You just only have to find them. And I'm giving here 2 examples, but there are other stars. So one is called Gaia Enceladus, which was discovered just immediately after Gaia came up. I will show you why. And the other is Sagittarius Galaxy, which was already discovered, has been eaten by the Milky Way. But now we have many more details about this galaxy. And look how beautiful it is. This is, for example, what has been first discovered. So Gaia, in the very small volume where the data is the best, 1 kiloparsec around us, where the dust doesn't bring much complications. So what people saw is that when they plot the circular velocity value radial motion of the stars, here is the disk of our Milky Way. Most of the Milky Way is here, but they start seeing this structure here. And this structure here looks like other stuff that was accreted to our galaxy. And this was called the sausage by Belokurov et al. 2018. As soon as the Gaia data release was out in 2018 too, Amina Helmi also had this in a velocity, because then she had the velocities. The velocities with also apogee data, a spectroscopic survey. She had this kind of plot. And here is a simulation and is what was being observed. Here you have the thin disk of our galaxy. And these in blue are stars that are in retrograde orbits. And this is a simulation where there was an accreted galaxy on the top of our galaxy. So she could model that, and essentially saying that the halo of our galaxy is being dominated by a retrograde population that is the reminiscent of an impact with Gaia Enceladus. She called it Gaia Enceladus. Today it's called Jazz. Gaia Enceladus sausage, because you had to put the sausage here. And now we have the Jazz, the Gaia Enceladus sausage. And the other data could constrain that this galaxy hit our galaxy around 10 billion years ago. This is amazing. How will we get this? From Gaia plus spectroscopy. And for that, you need distance, very good distance, which you have if you are in a small volume where you can invert the parallax of Gaia, and you don't have to worry much with extinction by dust. And she had also this, if you plot the chemistry of these stars. So this is a famous diagram that we explain in the lectures a lot. Alpha over iron, so an element produced very quickly by massive stars, an element restored a lot by type 1a supernova, which restore in longer time scales. And so if you are in an old system, usually this is high, and then this goes down because the type 1a enter into the game later. And this is what you see here, the thick disk and the thin disk of our galaxy, by the way. We're going to get back to this. And the Gaia Enceladus is here, part of this data here. And look, this is in the metallicity of the stars in a scale that I'm going to show quite often. 0 is solar, so like sun is here. This is 1 over 10 the sun, 1 over 100 the sun. So these are very metal-poor stars. Metals, for us astronomers, is everything that is heavier than hydrogen and helium. Okay, so Gaia Enceladus was a galaxy that collided with us, was big, and we know a lot about this galaxy, which is amazing. Another interesting thing is the fact that this is, again, the map of our galaxy towards the bulge, and here is the Kepler field. In this field, we have other observations that are astroseismology. And in these yellow stars here, so in this field there are stars, and these orange ones are the ones of Gaia Enceladus. Some are from Gaia Enceladus. And we measure the ages of those stars using another technique called astroseismic ages, and we reach 10% in precision for these stars, and we have shown the stars of Gaia Enceladus to be a bit younger than our own thick disk. So our galaxy was formed, had a thick disk when this galaxy collided with us. Now, this is beautiful, but we can do more. Another interesting thing is the Sagittarius stream. So the Sagittarius, the nucleus of Sagittarius, is a galaxy that collides with us and is behind the bulge, okay, that you saw in the map I showed. But the streams are left of this cannibalizing thing by the Milky Way. But if you look in a normal space, like high above the mid-plane as a function of radius, for example, the streams are difficult to see because the stars of Sagittarius are mixed with the stars of the Milky Way in the halo. However, because you have Gaia, you can compute things like the actions, which are constants of motions, because now you have you can compute energy, you can integrate the orbits, and you also have all the velocities. So once you do this job, you can go to another space where you find the stars of Sagittarius very easily. This space, for example, is angular momentum in the Z direction and in the Y direction, or this one that's very typical, energy versus angular momentum in the Z direction. And here, for example, I'm choosing only this parameter here, which says that are stars in predominantly radial orbits. And what I see here, these stars here in radial orbits that you see here are the Gaia-Enceladus stars, for example. So it's easier to select them. Now look what happens when I look only to the ones that are in polar orbits in our galaxy, accreting in polar orbits. When you do this, you see an excess of star here. This is easily to select. They are Sagittarius stream stars. And so I select them, and now I study them. And you have other populations you can select from other kinds of galaxies and streams that are falling in our galaxy. But let's take Sagittarius, because you have a lot of them too. And now you will be able to tell the story. In this case, I'm using Segway data. It's one of the Sloan survey data. And only by selecting this, it was already possible for the first time to have very metal-poor stars in Sagittarius found, and also to have ideas about how was this galaxy before accretion. And it looks like this galaxy had already a gradient of metallicity. It's so crazy. Something that was accreted more than 8 gigayears ago, and I can tell what's the structure. I'll show you in a while. So here is the Z, and so here is our galaxy, the bulge. Here's the disk design. Here is the core of Sagittarius dwarf. And this is our streams. It's a model of the dark matter and the stars of Sagittarius accreting streams in several passages. And here, these data points, the red and the blue, are the trailing and the leading arm that are passing next to the sun. And now I can select them, because, of course, they are mixed to the halo. And once I select them, I can found in this data set a lot more of metal-poor stars here. This is their metallicity, 1/100 the solar. I found a lot of metal-poor stars. And I can also check the ages of these stars in the trailing and the leading arm. So it's amazing, because to get an age of a galaxy outside is much more complicated than doing this. So we provide here, with this example of one file we had, we provide the first age estimates for individual stars in the Sagittarius streams, thanks to this sample that were sitting in a place of the color magnetodime where we could get good ages. And we got an age for these stars of around 11.7 gigayears old. And also you can trace the alpha over iron versus iron. Here is the thick disk of our galaxy, because it stops in metallicity is more metal-rich. Here I'm just showing 1/10 the solar metallicity below. And you see, here is our halo. This is the stars, the tracing this chemical evolution here of the stars in the Gaia-Enceladus. And this is the trailing and the leading arm of Sagittarius. Each one sits in a different place of this, and you can, with that, give it the history of the star formation history of those galaxies and understand their enrichment. And it's crazy, because it's an outside galaxy falling here long ago that we can find, and we can do all that. Okay, the other thing I wanted to show you is related to the age of the thick disk. You saw the thick disk is a bit more metal-rich, so it was outside of that plot that I show you with. Once you pass -1, when you go below -1, you have a lot of these accretion events from the halo that you can easily find. When you enter in -1 and more metal-rich, so solar, like our sun, or 10 times, up to 10 times less than the sun, now you have a mess, because now you have the Milky Way, and on the top of Milky Way, whatever accreted as well. Because it doesn't mean that only the metal-poor accreted. There is also accretion in the other, but it's more difficult to find. So the first thing I wanted to explore here is the thick disk of our galaxy. And that's very interesting, because when you plot this alpha over iron versus iron plot, which is the basics of our galaxy, you can use this as a, let's say, a clock, more or less. The people that are here in this plateau are old, and this is younger. This is the general picture of the clock. But if you have seismology, you can determine, in that field that I show you, of the Kepler field, you can determine the age is very good for individual stars. And then now what do you see? These are stars that are here around us, but now 1 kiloparsec, more or less, in the Kepler field. And this is colored by age. And you have here, the high alpha is, in fact, old. And in the thin disk, this is the thick disk, and these are the thin disk stars, you have a dégradé, showing that the youngest are here, the oldest are here. However, when I get very metal-rich, so the sun has this metallicity, when I get 2 to 3 times more metal-rich than the sun, I start seeing that actually they are not the youngest. They should, because how the metallicity increase? The metallicity of the universe increases with time, in principle, because you have several generations of stars processing this gas and enriching this gas. So in a naive idea, the end point of this here at the solar vicinity should be the youngest stars. And the data is telling you it's not, okay? These stars are actually old, and metal-rich and old. So this tells you the stars came from somewhere else. But let's go, this is in the thin disk. But let's see what the thick disk ages told me here. And with this time, we could have a very, very good age. So we had the age with 20% more or less uncertainties. And when you plot what we call the probability density distribution of the scattering age of this thick disk population, we see that the thick disk population is coeval. Is done in 1 gigayear, is done. So you understand the high alpha population, which is, I'm calling here the thick disk of the Milky Way, has a very small scattering age. And this is meaning that this is a coeval population forming in less than 1 gigayear. That's what this means here. Okay, so now you have these maps that I show you, and in this square here, you have the bulge and the bar of our galaxy that you can see there. However, from these 30 million stars, you only have 30,000 for which you have spectra. These are the spectra, and these are the apogee spectra. So we computed here, for the spectroscopic surveys recently, distance for 11 million stars, from which 2.5 million we could compute ages. And it's part of this age that I show you with the results of Sagittarius. In the case, we had also age for Sagittarius. So when we now look to the age for these other spectroscopic surveys, we ask ourselves, do we get the same answer? And this is what we get when we look to the other surveys. If I use Lamoste, this is the age I'm getting for the thick disk. Gala, other spectroscopic surveys, I'm getting very similar ages with very small scatter in the age. And these are the typical V phi, so the velocity of rotation in the disk, showing that this is thick disk because it's lagging the thin disk. The thin disk rotates faster, 220 kilometers per second here, and this is lagging, so it's really thick disk and have this kind of velocity dispersion. Okay, so I can understand then this dichotomy, the high alpha and the low alpha as the thick disk and the thin disk, and there is a discontinuity between the two that we believe it was a quenching of the thick disk, and then you form the thin disk. The quenching of the thick disk meaning the thick disk, as I show you, has a very coeval and stopped being formed after 11 gigayears, something old. And the thin disk would form later. However, turns out that's not that simple. When we were happy and confirmed. So it starts to appear many data. Imagine here is, you have the orbit of stars, and now you see the Zmax, how high from the midplane a star can reach in its orbit. And here's the eccentric orbits. And people expect that when you go to very metal-poor stars, really like -2, -3, you should be only having halo. Nobody should be turning in a disk orbit, okay? Because halo is a high-velocity dispersion population, so you shouldn't have anybody here. But there seems to be a residual of stars that are, even though I'm in very metal-poor here, people start seeing some stars here that are turning like the disk. Okay, then the people say, oh, this is important because at the same time, JWST, which is looking at very high redshift galaxies, is finding large disks already in place at redshift 4, which is not expected as well. Well, it was not expected, but it is. There are disks. Now, the people, when they start finding metal-poor stars in thin disk orbits in the Milky Way, said, okay, we are also seeing at high redshift. But it's not expected in the sense that the current theory was that the thin disk was not that old. First, you form the halo, then the thick disk, and after the quench, you form the thin disk. That's the kind of the story of the Milky Way. So these stars in the metal-poor and in thin disk orbit disturbs this scenario. And the idea was like, okay, first of all, the excuse was the disks we are seeing at high redshift are not the progenitors of the Milky Way. they are progenitors of heavier galaxies, other kind of galaxies. So we shouldn't expect to see this. So no problem. The ones that you are seeing here, metal poor and in disk orbits, they are a dynamical effect that some stars from the halo are captured by the bar and then thrown here, for example. And so this is a dynamical effect. If it's a little bit of stars, you can go away with this explanation. When you start finding more and more and more, then it gets more complicated, especially if those are not metal-poor stars, but are metal-rich stars, okay? So this is what happened. People start finding, one of them was the Belazzini et al., 2024. So all this that I'm talking from now on is happening now, between March, May, June. You know, we are in this rush of papers and letters like in last minute. So essentially, Belazzini et al. Found, there were some people find a couple of stars, and they used some Gaia data and found some ideas that more metal-poor stars were having disk orbits, okay? But it was discussable because the data didn't have enough radial velocity or other information. So essentially, there was a need for a large statistic to see if this was really happening. And more or less, if we have those stars with low alpha also that are so old and they are not expected to be there. Okay, that's where it enters our data. As I show you, we are using a code to compute using Gaia information, spectroscopy, and photometry, distance and to stars. However, the Gaia data has been evolving. So the Gaia data from Gaia DR3 is better than Gaia DR2, better parallaxes. In Gaia EDR3, you have also better proper motions. When it came to Gaia DR3, they released also RVS spectra, which is low resolution spectra, okay? And if you take, and they analyze this spectra and put out the stellar parameters we need, the temperature, log G, metallicity, and so on. However, if you analyze this spectra, because this spectra is a lower resolution spectra, if you analyze in the standard way, which is what the Gaia group did, it turns out that from most of these spectra, the signal to noise is very small, very low. And so most of the spectra for which you got good data are from high signal to noise. And the samples shrink. So they did millions of stars, but if you use the signal to noise cut, you end up with a very little amount of stars, so it doesn't help. So what we did is that we combined a way to analyze the Gaia spectra with a machine learning thing that's called convolutional neural network. And why we did that? Because when you came Gaia DR3, it came not only, and Gaia DR3 came in June 2022. This is the time that it takes you to come up with, to use this data, you know? And so we said, okay, what else they gave? They gave the XP spectra, XP coefficients. This is another information that is like a small filter, okay? But in coefficient way, we had to find a way to use it. Okay, we found a way to use it, and this is called our better RVS, which is from Gaia, CNN catalog, where we use a lot of information, and in this way we could have 800,000 stars with very good parameters sitting next to us, because the RVS spectra of Gaia is for bright stars, so sitting around us. However, now we have exquisite data set, because here around us is the best parallax of Gaia. And so we achieve an uncertainty in distance of 1% for these thousands of stars. And with 1% distance uncertainty, you can get amazing luminosities. And with that, you are in the game to say also for a particular group of stars, which are in the part of the CMD or that give you, I don't want to say CMD because if people don't do astronomy, the part where I can use models to fit the data that can tell me the age. That's what I mean. Because if the star is in another part of this diagram, I cannot tell the age like this. So that's what we are going to use, this. And then we're going to check what we see in this data. Because another thing that you see that this data do, this is the data. So now here is the solar vicinity. this is the new Gaia data. Now you see that I'm very small in volume, but exquisite data. And here, this red group here of stars is for the ones that I have amazing ages. Okay? So when I look this, immediately I have something very nice from Gaia. Gaia took the spectra from the space, so I don't have a lot of complications that I have in the spectra in the ground. And the Gaia has arrived very close to the mid-plane. Previous spectroscopic surveys are like a cone, and they lack the mid-plane. I have this, because I have also the north and the south, because usually the spectroscopic survey is taken from the north and taken from the south. Gaia is all sky. So I have several advantages. Among this sample, I have 200,000 stars for which I can have ages, which is amazing. This didn't exist before, okay? With precise distance. So what happens now? This is galactic-centered. This is the outer part. Our sample is solar neighborhood, more or less. And this is the map of our galaxy. What do we see? Now, it requires a bit of patience to see this. Velocity of rotation. People like our sun are sitting here. The solar, we turn the galaxy in 220 kilometers per second, more or less, okay? And now, when I go metal poor, so metal poor, 1/10, 1/100, what do I see? I see these black people here. They are metal poor stars turning at 220 kilometers per second here. It's not a couple anymore. It's a lot, okay? Many of them. But still, people could say, but they are being put here by some other process. They are not the old thin disk of the Milky Way. Now, I should stop here because people are using the metal poor as the older. They are the oldest because they have no chemical elements yet. They are very pristine. And they never look here inside because there is this preconception that who is metal rich cannot be old. And it's wrong. And so now we have age, so we're going to enter this cloud here. And when we enter this cloud, where people haven't looked yet, look what's happened. With ages, by the way, the people that do not turn or are in a retrograde orbit are here. The Gaia Enceladus, I show you, the Sequoia, which is another galaxy, okay, in this diagram. Now we're going to enter into this place here, which was forbidden before because it didn't have ages. Okay, so when I do that, I need ages. I will find, but before I do that, I have to tell you that. At the same time, we found what I'm going to show you, another sample of people using an object that's called RR LiDAR found stars with thin disk orbits. This is a tumoro diagram. The stars that are inside here are turning at 220 kilometers per second. They are thin disk, thick disk, and halo. And if they fall here, they are retrograde, and they are the Gaia Enceladus. This RR LiDAR, at the same month the same date we put ours out, this paper, using GALA, they found these stars here. Why is this important, RR LiDAR? Well, the RR LiDAR are objects that are older than 10 giga-year. There you don't have a problem to compute the age. They are older than 10 giga-year. So there shouldn't be so many old metal-rich stars here. But we didn't know about each other, okay? And we are afraid of our age. They are not afraid of their age, but they are afraid of other things. So they're also having problem with referee and so on. Now we look to our thing, and if we plot alpha over iron versus age, like I showed you before, the low alpha was the thin disk, and then the high alpha was the thick disk. So it should be thick disk, nothing, thin disk. That was the idea we had, okay? But you are seeing thick disk, thin disk, but there is a lot of stuff here. You see this? These are old stars with not solar alpha, but a little bit lower, but very old. What is this? Because this is thick disk, this is thin disk, and the idea was that you had the thick disk, you had a quench of this population, and then you form the thin disk. But these people are telling, no, it's not true. We are there. Of course, to come and believe this data, you have to believe your age, and the age is tricky. So I have seen this tip of the iceberg in other data sets, and I never had the courage to claim that we are seeing a very old thin disk of the Milky Way. And this we claim, because here we got age 10 to 15% precision. And it's enough to claim that we believe the stars that are here, okay? And we have a lot of stars. So what is this? The old thin disk of the Milky Way. The Milky Way disk was in place immediately after Big Bang, 1 gigayear after the Big Bang. Now, usually when you have a data like this, you better find the age computed in a completely different way, because then if you find again the same result, it's a good thing. And we have the project where we are computing with Kepler and Apogee using another technique of individual oscillations from seismology, which give you precise age. As I told you, in this Nature Astronomy paper we had, it was because the precision got so big that we managed to precisely date the Gaia Enceladus age. So we are using the same technique. This is not published. And this is the same diagram. Alpha Verarum versus age. We see our thick disk, again, that I show you, is coeval, around 11 gigayear, is there. But we see some stars here. This sample, we lack statistics. So this, I have thousands of stars. The other one, I had 100,000 of stars. But I have a very good precision for a completely different technique. And the field now is in the Kepler. So it's not down into the disk, it's in the Kepler. So I have less number of stars in the thin disk. So all these problems, but it's not empty here. You see? You see that too. Okay. So we can go beyond that and say, okay, let's compute the velocity dispersion. The velocity dispersion is how much chemically hot is this population, right? So the thick disk, as I showed you before in the first data set, has a velocity dispersion of around 40 kilometers per second. These are the points I had shown you from this other data set I worked in the beginning, Kepler, Milky Way, Apogee. And look how interesting. These red points here are, this is our point, and this red point here are, these are the data set I was showing you, because this is not published yet, that's why I'm like this. So don't photograph. This is the thin disk, the low alpha, this is the high alpha, and there is a velocity dispersion difference between the two, first of all. And this is our other data set, the data set is published, that we have the same. High velocity dispersion, low velocity dispersion. But of course, the velocity dispersion increased a little bit. We have the thin disk going very old age, and on the top of it, the thick disk. Same thing here. And here, these other data points that you are seeing here, the red points in this one, are, the brown points, are the galaxies we see at high redshift. If I take the velocity dispersion of very high redshift, I also have some disks that are quite cold and others that are a bit warmer. I have thick disk and I have also cold disks at very high redshift. These are, for example, this data at Z 4.5, redshift 0.4.5 from Rizzo et al. Group into 2021, but there are others. So essentially, the two data sets, which come from completely different techniques, completely different stars. One are main sequence turn-off dwarf stars. The other are giant stars. They are telling us the thin disk of the Milky Way was very old. It's not that you had the thick disk and then a gap and then from the thin disk, okay? And this is important because it turns out that the current cosmological simulations forming disks have usually trouble to set the disk very early on. Most of the simulations of Milky Way-like galaxies, which is also a complicated thing to do, most of the simulations start with a very hot population, high velocity dispersion population, which in the Milky Way was called the aurora population. And then you need time to settle in a disk. And then you start the thin disk. So the high redshift data is showing that you have already some in-place disks. And in the Milky Way, we are finding very old stars in thin disk orbits. Now, the Milky Way is more problematic because they have to be in thin disk orbits and continue in thin disk orbits, which is not so easy, right? Because we were kicked, as I said, 10 gigayears ago by Gaia Enceladus. So that means that maybe this disk was very inner, in the inner part, and the stars, olds that I'm seeing, are also migrated here. That's where we are discussing now. Some people believe this old disk of the Milky Way and myself, I'm doing another paper now to see if those old stars could have been formed in the inner parts of the galaxy, in the bulge, and being ejected here by the bar. However, their structure is too much thin disk. It's very hard to find all these explanations. It's okay if you have a couple of stars, but we have thousands of stars with high precision ages. And so that's why if you go to our institute, www.ip.de, you see that the press release of this month is our paper, because this is important. And for example, very recently, I'm going to put this as one example. You have a paper by Madao and co, where they are exploring the formation in some simulations of very early thin disk stars. So essentially, the Milky Way can give observational constraints to also early cosmological simulations, and bring it to the debate all this that is happening. And so that's what I wanted to show you. I think, yeah, 47 minutes is enough. Otherwise, you guys get too tired of this.
Thanks a lot. Time for questions.
So I had two questions. How do you estimate the precision of your age measurements?
Yeah, so that's the whole paper is about that. Essentially, in this case, we have the CMD, where we are taking the main sequence turn-off subgiants. So what has happened, and that other groups have not seen this, is because they have a stick to the subgiants, and we extend to the main sequence turn-off. And if you do not extend to main sequence turn-off, for old metal-rich stars, you're going to not see them, because they are not going to arrive in the subgiant phase. So what we did is, like, first, we have very good stellar parameters for this sample. Then we obtained it with a spectral photometric code that is a Bayesian code, which included the photometry with the errors, the spectroscopy with the errors, the parallax with the errors. It's a Bayesian approach, and spit out the PDFs of the ages, the probability density distributions. And when we look to these PDFs, the uncertainty is around 10 to 15%. Of course, when you get to if you put age for the universe, if you put in the system that you say the universe is 13.7, then of course, when you reach that age, you cut the PDFs, right? And so you may think your uncertainty is smaller than what it is. So we explored that too, rerunning the ages and leaving the age of the universe free to see if we still get the same kind of uncertainty, and we do. And then we did other things, like, for example, do we trust these ages? And so we have in the Milky Way something very interesting that's called the cosmic clocks. If you take a weird element, yttrium over magnesium versus age, is showing in the Milky Way that there is a relation. Because yttrium is making one time scale, magnesium another one, and it's a beautiful relation. And this relation had been shown for some stars up to a certain age. And we show that our stars fit perfectly that relation. So it's giving to us to believe that this age is trustful also. And these are the things we test. But so I believe the uncertainties are under control here, around 10, 15%.
The other question, I'm not from the field. How much of the Milky Way is dark matter, and why does this affect your analysis? Or?
If the dark matter of the Milky Way affect this here, not really.
So how much of the Milky Way is supposed to be dark matter?
The total mass of the Milky Way with dark matter, 10 to the 12, right? Yeah, that's the question. Is a bit complicated because it depends where I am, right?
But is it 50%, 20%, 80%?
Yeah, it's 50%.
So 50%, but that doesn't affect your analysis because you don't obviously.
No, we are using, of course it does, because I'm computing orbits in the end, right? And so I use a potential. And the potential is assuming several things, among them also essentially the dark matter. However, after the Gaia data, also the mass of the Milky Way could reach another precision also in terms of the values that we have, because you can study the orbits of several stars and you can get better hint of the potential. The potential is still very problematic when I am in the bulge of the Milky Way. But here is kind of trustful, hopefully.
More questions?
Yeah, thanks. In the last slide, you showed that the heavier stars have like a bigger fluctuations in the velocity, because the metallic ones, right?
This one?
No, yeah, and
This?
in that one, yeah. So, because if I think in the Maxwell velocity distribution, the first that comes to my mind, the variance is inverse proportional to the mass of the object, of the particles that you are measuring. So, how is possible that more heavier stuff have a bigger variance in velocity?
Why are you saying heavier? I don't understand.
It's not metallic?
Now, each point here is a bunch of stars.
Okay.
Each point are stars. Think it as a one star, typical. Because for each point I have a bunch of stars, so I bin it. So it's not a galaxy, it's a star. And so it's not, they are not more heavy or not heavy. This is just stars at different ages with different orbits. And the ones that are older, they tend to be, if they are in this low alpha population, if they are in the thin disk, they tend to be a little bit in more hot orbits, so they go to, I don't know, 30 kilometers per second, or 25 kilometers per second, compared to the very young ones. The very young ones, stars, they are born from the molecular clouds, and they start with something like 10, 20 kilometers per second, and then they get heated by their evolution, and then you get more velocity dispersion with age, right? This is normal. What you see in the thick disk is a jump in velocity dispersion. It's not a continuity, it's a jump. The thick disk really has very high velocity dispersion. That's why we believe the thick disk in our Milky Way is a separate thing than the thin disk. It's another thing. How it formed, there's a lot of discussions of that too. But so that's why what was not expected here is the blue curve continue after 10. That's what's not expected. Okay. That I have something between 10 and 13 there where the blue curve is. We were expect to see the red, nothing, the blue.
Okay. Okay. Thanks.
That would be, actually, this is a result against my own result, which because in my PhD, I made the two-info model, which still holds in some sense, which two-info model was to explain this dichotomy in alpha over iron, that there was not a link between the thick disk and the thin disk, but the fact that I see a high alpha and a low alpha separated means that I had a quench in the star formation after the thick disk. So that's why I transformed that chemical plot into a star formation history plot, and became very known this thing. And he said there was a quench. In the info model, there was a sequential situation. You had the thick disk, you quench, you form the thin disk. And what the data is telling me, yes, there is the quench, but it's not a sequential formation. The thin disk was there already being formed. And this is interesting.
Okay, so first, very nice talk. And secondly, I have two questions. The first one is, well, then the thick disk is quenched, as you say. So
Yeah.
first question.
What's the thick disk?
No, what's the what's the quenching process that we're thinking that, you know?
Okay.
And, yeah. And the second of all is, if there is no discontinuous, as your results just have shown, well, then I imagine this quenching process is like still going, or am I wrong to think about that? Yeah.
So, yeah, okay, thanks. So, this is very interesting because my job in galactic archaeology is to tell you the thick disk was quenched. The data is telling me this. I'm not running a simulation. I'm not doing a chemical evolution. I'm just saying thick disk is coeval. Now, it takes the people doing simulations to figure out how. No? And we have here a person that can probably have his own ideas about the thick disk. But there are different kinds of simulations. There are different reasons why it's quenched. I have a full list, okay? So, for example, some Auriga simulations think that at some point the thin disk shrink and the gas disappear and you quench this thick disk. There are some simulations, cosmology simulations, where a lot of galaxies have this dichotomy, high alpha and low alpha. There is, and it's never clear to me exactly why. Then there is another group of simulations where only 5% of the galaxies had the thick disk and thin disk. So some people want the thick disk to be essentially formed by radial migration. I don't believe that, because by radial migration you do not achieve velocity dispersion that high. It has to be something else. But you could essentially think about a big merger event with our galaxy. So that could be Gaia Enceladus making the thick disk. But doesn't work because this is high alpha. And the oldest thin disk we are showing is not that high alpha. Okay? So it's getting more complicated, I would say. There are different ideas, different simulations. People think that they have the answer. So far, I haven't seen one answer that convinced me that this is really the answer. Okay? There are some simulations where in the beginning, when the gas is collapsing, it's too hot, in the sense it's too turbulent. And therefore, you never really form the thin disk. You already form it thick by the start. It's not a thin that became thick. It's a thick by the start. I believe that is the solution. And at the same time, you're forming the thin disk because the gas can come from the borders of the Milky Way, you know, and forming the thin disk in a different process that while you are forming the thick disk. So this seems to me a good explanation. But there are other groups that wants that the whole thick disk was accreted. It's difficult, because when you saw in the lecture the alpha-over-iron ratio all over the disk, right? It's very internal only, this thick disk. So, yeah, maybe. I'm open. It's the data that's going to tell, because it's very difficult for the simulations from first principle to answer everything. So it's a feedback talking between us and them, you know, to see what's the best.
More questions?
So you said something that people believed, I believed that, and then you said it's wrong, that metal-rich stars are young. And I said, no. Now we know that the metal-rich stars can be very old. So how come? How can they get the metals if they're very...
No, so there is a difference between metal-rich and super metal-rich, okay? Yeah, so sorry, I didn't say that. So when we, in this alpha over age thing, we see that when we are approaching solar, if you take the sun today, there is a beta list, a value, solar. And if I go to the gas and measure a H2 region, the gas today from emission lines, it's essentially the same metallicity. Yeah. And so that's what's telling me. That's telling me that star formation in this position was very inefficient. By the time the sun formed, the thing was already down and didn't enrich much the interstellar medium. Now, that's okay. Today, the gas is not so enriched. But now, I see the stars beyond that metallicity, a bunch of them, and they are called supermetal-rich stars. Those are the ones that were not forming with the star formation history of this position. They have to be formed somewhere else, where the star formation was so strong and fast that I could enrich very quickly. And then they migrate, yeah. And now, I didn't have the time to show, but in the lecture I will show, in the same data set that I have looked down here for the thin disk stars, the first letter we have, which is also a press release in, there was an article also in Scientific, what's this American magazine, they interview us, is because we also got in this sample a huge amount of supermetal-rich stars. And we said, let's look what these supermetal-rich stars are doing. And when we look to them, and I will show this in the lecture tomorrow maybe, we computed the orbits for these supermetal-rich stars, but now we are not talking about 1,000. We are talking about several thousands. And I compute the orbits, and if I plot the guiding radius of the orbit, the mean position, because the star may be in HGS, so it's passing here, but it's from another guiding. I plot the guiding radius as a function of metallicity. So I plot the guiding radius of the whatever metallicity, and I go like this. By the time I cross this point, point 2 more or less, I see that all the metal-rich stars start showing peaks in guiding radius. They are linked to the resonance between the bar and the spiral arms of the Milky Way. They are sitting on the resonances, you see? This is so beautiful. And this is, you just see them, just look to this data set, and then you see the supermetal-rich sitting in the resonance. You can even trace where they are, the resonance in the disk. So this is very beautiful. Before we did in the letter with thousands of stars, now we have a new data set where we look to the same thing for 7 million supermetal-rich stars. It's amazing. Yeah, so now it becomes difficult to say, no, I don't believe, you know. It's a very nice moment.
Some more? Okay, if not, we can thanks Cristina
you.
again for the nice colloquium.